welcome back.
Hey, that's my line. Well, back to business. Today we're going to continue talking about electromagnetic waves. And this is a topic that we've talked about in class already, where we've taken Maxwell's equations in the differential form, that is Maxwell's equations as they describe fields and what's happening to them at points. And we combine three of Maxwell's equations to show that the electric field obeys a wave equation. In this case, I'm parameterizing that wave equation as a wave traveling in the z direction. And so the electric field is some vector that we called E naught, which represents the amplitude of the wave in the x component, the y component, and the z component of the electric field. And then the part that looks like a wave, the cosine of z minus zt. And since we chose our wave to move in the z direction, then I can combine that with another one of Maxwell's equations, that the divergence of E vanishes, to find that the vector of amplitudes, E naught, has just two free components, E naught x and E naught y, because the divergence of V vanishing requires that z component of E is identically zero. And so what we did was we said that the electric field has a wave solution, and the component of the electric field in the direction of the wave always has to be zero. And what we're left with are two free parameters, which are the magnitudes of the electric field in the other two, the amplitudes of the electric field in the other two directions. Those are known as the polarization vector, right? And they tell us they tell us in that orthogonal two-dimensional space where the electric field is. But we can know more about this because so far we've only talked about electromagnetic waves as waves in the electric field. But of course, Maxwell's equations help us to tell the difference, to help us to relate the electric field to the magnetic field. And so if I already know that if I have an electric field that's changing or a magnetic field that's changing, then that's going to tell me about constraints on the other field, right? So if the curl of E is equal to minus dV dt, and I know that the electric field has some derivatives associated with it, then that probably means that the magnetic field has some time derivatives, and therefore the changes in the magnetic field are related to the changes in the electric field. So let me take our plane wave ansatz, where I have a plane wave going in the z direction, and rewrite it as a single vector where the electric field is equal to E naught x times the cosine, E naught y times the cosine, and then 0, because there is no component of the electric field in the direction of the wave. I can plug that into the left-hand side of Maxwell's equations to get the curl of E is equal to equal to these two components. The x component is minus dEy dz, and the y component is dEx dz. And so both of these only have derivatives with respect to z, of course, because my function only depends on z. And so all of the other derivatives in the curl are automatically 0, and I'm left with only two terms. That, of course, has to be equal to dB dt. So I have a vector equation, right? I have, in principle, three components on the left, although the z component is 0, and I have three components on the right, which are differential equations for the components of the magnetic field. That means that this equation is really three different equations that I can perhaps use to solve for the components of the magnetic field, given some solution to the electric field. So let's do it component by component, okay? Term by term. We'll start with the easy one. I know that the left-hand side had no component in the z direction. The right-hand side is minus dBz dt. Of course, combining these two things only tells us that the z component of the magnetic field has to be a constant. Okay? Maybe I have a homogeneous magnetic field. Maybe I have a magnetic field that's something else. I don't know, but it can't be changing with time, right? And so the easiest choice, unless I know that I have some homogeneous magnetic field in the background, is to choose that constant to be equal to 0. After all, I'm talking about the vacuum solutions to Maxwell's equations, and so perhaps there aren't really any magnetic sources anywhere nearby, and I can approximate any homogeneous field value in the background to be 0. Great, we're 1/3 of the way done. Okay, let's do it for the x component. So first, what I have is that minus the derivative of Ey with respect to z is equal to minus the derivative of bx with respect to t, right? The x component of the curl of E actually contained the y component of the electric field, and that's why I have a dy dz on the left-hand side. But on the right-hand side, I just had the time derivative of B, and so I still have the x component. If I take the z derivative of the electric field, which I've drawn up on the top of the page here just so that we remember it, I have the derivative of a cosine, which is a minus sign. That gets rid of this minus sign over here, times sine of z minus ct. And since I'm taking the derivative with respect to z, I don't have a chain rule to worry about. On the right-hand side, I just have minus dbx dt. Now, when I look at this, I want to solve for the x component of b. The sort of most straightforward thing to do, which is the thing we're going to do, is to just integrate both sides with respect to t, right? And then I can use the fundamental theorem on the right-hand side, and on the left-hand side, I just have the integral of sine, which I know is going to be a cosine. And so if or it should be a minus cosine. So if I do that integral, of course, I have to do a u substitution on the ct, which gives me another factor of minus c. Well, what I end up with is that the x component of b is going to be equal to minus. So there are many minus signs to worry about, so let's make sure we do them all, right? So I have a minus sign that comes from the relative difference from the left and the right-hand side of the second line. I have a minus sign that comes from the antiderivative of sine, and I have a minus sign that comes from the u substitution for u is equal to ct. So that's three minus signs make a minus sign. So bx is equal to minus e naught y over c times cosine of z minus ct. Wow, this really looks a lot like this, right? That the y component of E looks almost identical. It's in phase to the x component of B. There's this minus sign, but so it has the opposite shape, but they're in phase with each other. And the amplitudes are also, they're just proportional to each other by this factor of c, which is the speed of light, which is really something that tells me about the units, of course, that I'm using to measure both of these fields. This is true for the x component, that the x component of B then is related to the y component of E. If I did the same thing for the y components, I would get that the y component of B was equal to the x component of E divided by C. Okay, so I get this coupled case where the x component, the constant, the x component of B is equal to minus E naught y over C, and the y component of B is equal to the x component of C, right? So there's this exchange between x and y components with one extra minus sign, and that extra minus sign actually makes it so that my polarization vector, whatever it is, so I'm going to draw it over here, my E naught polarization vector points in some direction, then my B naught polarization vector is always going to be perpendicular to it. Right? That minus sign, and when I switch the entries and I add the one minus sign, what I'm doing is I'm creating a polarization vector for the magnetic field that's exactly perpendicular to the polarization vector for the electric field. And when I write them out, I can see this a little bit more explicitly. The x and y, the x component of E is the y component of B, and the y component of E is minus the x component of B. I always have that perpendicular relationship between the polarization vector for E and the polarization vector for B. But most importantly, this is a fully constrained system. That if I have the polarization of E, then I absolutely have the polarization vector for B. I don't have any choice for choosing new free parameters in this case. I have the polarization vector for B. So the last thing I want to talk about is something called the Poynting vector. Okay, it's spelled a little bit funny, but actually it has a great name because the Poynting vector is a vector that we construct that helps me to understand where the energy in the electromagnetic field is going. So I already know that the electric field and the magnetic field are going to be perpendicular to each other, and I know that they're both perpendicular to the direction of motion. right? So if I had, in the case that I was looking at, I had a wave going in the z direction, and both the electric and magnetic fields were in the x and y direction. So there was no field in the direction of motion. The Poynting vector then takes that into account and says, well, if you take the electric field and you cross it with the magnetic field, you have a Poynting vector that points in the direction perpendicular to both of those fields. And the way it's constructed, it will always point in the direction that the energy is flowing. So here are your take-home messages. Maxwell's equations have wave solutions, and I get those wave solutions by looking at combinations of Maxwell's equations until I get a wave equation. By using other Maxwell's equations, I can put constraints on that wave equation, or the solution to the wave equation, and I can tell that the electric and magnetic fields have to be perpendicular to the direction of motion of the wave. And I'm always left with two free parameters, which we usually put in the electric field to measure the two different perpendicular components of the electric field. And then I have a Poynting vector, S, which points in the direction of the energy motion, and the units of the Poynting vector turn out to be how much energy is there flowing per unit area, per unit time. And the Poynting vector, because it's perpendicular to E and B are perpendicular to the direction of motion, all of the signs work out so that we've constructed an object that really tells me about how the energy is flowing with the electromagnetic wave.